Hi, I'm Jana Ibrahim, and in this video, we will discuss about operational amplifier or op-amp. What is an op-amp? Op-amp or operational amplifier is an integrated circuit IC that amplifies the difference between two input voltages and then produces a single output. Op-amp is very popular in analog electronics and is considered as an electronic device such as BJT or FET. A bit of history lesson: in 1960s, the term operational amplifier arises due to the original application of the device. Op-amps were used in analog computers together with resistors and capacitors to perform mathematical operation, including the differential and integral equations. In this video, we will discuss the ideal characteristics of op-amp and analyze ideal op-amp circuits. From our previous discussion of amplifier characteristics, one of the key aspects of performance that characterize any amplifier circuit is the gain. This also applies for the op-amps and op-amp electronic circuit design. An op-amp on its own offers a huge level of gain when used in an open-loop configuration. There are two conditions that can be considered when looking at op-amp gain. First, open loop gain. Ideally, for open loop gain, the gain A is equal to infinity, and this form of gain is measured when no feedback is applied to the op-amp circuit. In other words, it is running in an open loop format. In reality, in this configuration, gains are normally very high, typically between 10,000 and 100,000. This is the gain of the op-amp on its own. In an open loop condition, ideally, the input resistance Rin is infinity and the output resistance Rout is 0. However, large gain variations, even for the same type of op-amp, can occur as a result of the fabrication processes used. Whilst op-amps themselves offer huge levels of gain, the gain is seldom used in open-loop condition to provide signal amplification simply because it would be very difficult to utilize. A small input signal would drive the output to beyond the real voltages, which results in limiting or clipping of the output. Therefore, by using a negative feedback within the electronic circuit design, the huge levels of gain can be used to good effect, providing flat frequency responses, low distortion, and very defined levels of gain for the overall circuit, not dependent upon the actual gain of the IC, but on that of the external components whose value can be accurately chosen. The other condition for op-amp is the closed-loop gain. This form of gain is measured when the feedback loop is used, creating a closed loop to the circuit. By applying negative feedback, the overall gain of the circuit is much reduced and can be accurately tailored to the required level or to produce the required outputs, as in the case of filters, integrators, and etc. A few electronic components like resistors can be added to the op-amp circuit to provide the required feedback. In other words, the op-amp will have sufficient gain, or the gain of the overall circuit defined by the negative feedback and not by the gain of the op-amp itself. Although negative feedback is normally used for analog circuits, there are instances where positive feedback is used. The most common application of this is for comparators, where the output is required at one of two levels. This mid-trigger is one example where hysteresis is introduced into the system. In these applications, comparator ICs should be used rather than op-amps because they are designed to operate in this mode. In other op-amp circuits, the feedback may be used to provide other effects such as filtering and the like. One aspect closely associated with op-amp gain is the bandwidth. The huge gain of op-amp can lead to instability if steps are not taken to ensure that the op-amp and its circuit remain stable even with negative feedback applied. In its basic terms, a small capacitor is added to the internal elements of the op-amp, and this has the effect of reducing tendency to oscillate, but it also reduces the open loop bandwidth. But this aspect is not covered in this video. Here, we will be covering the inverting and non-inverting amplifiers. Negative feedback is used to control the gain of the overall op-amp circuit. There are many ways in which the feedback can be applied when designing an electronic circuit. For example, it may be independent of frequency, or it may be frequency dependent to produce filters. The two simplest examples of op-amp circuits using feedback are inverting and non-inverting amplifiers. The circuit for the inverting op-amp is shown here. This circuit has the output 180 degrees out of phase with the input and also provides a virtual ground. The op-amp circuit is quite straightforward using few electronic components, a single feedback resistor connecting from the output to the inverting input, and a resistor from the input of the circuit to the inverting input of the op-amp. Note that the non-inverting input is taken a ground point. This op-amp inverting amplifier circuit uses only two additional electronic components, R1 and R2, and this makes it very simple and easy to implement. Let's derive the inverting amplifier gain equation. As far as our calculations are concerned, the input to the op-amp itself at the inverting terminal has no current, or In equal to 0. Well, this is because of the impedance of each input terminals, inverting or non-inverting, will be well above 100 kilo ohms and possibly well over 1 mega ohm because of ideal op-amp condition where Rin, or the input resistor, is equal to infinity. Hence, any current flowing into the chip can be ignored, or In equal to 0. From this, we can see that the current flowing in the resistor R1 and R2 is the same because no current is flowing out of the junction between the two resistors, or at node G. And by using Ohm's law, we can write V out over R2 will be equal to minus V in over R1. Hence, the voltage gain of the circuit AV can be taken as AV, or V out over V in, will be equal to minus R2 over R1. Next, we discuss about non-inverting op-amp gain. The circuit for the non-inverting op-amp is shown below. In general, it offers a higher input impedance than the inverting op-amp circuit. Like the inverting amplifier op-amp circuit, it only requires the addition of two electronic components, which is two resistors, to provide the required feedback. The non-inverting amplifier has the characteristic that the input and output are in the same phase. This is a result of the signal being applied to the non-inverting input of the op-amp. Let's derive the non-inverting amplifier gain. For the purpose of our calculation, the input to the op-amp draws no current as the impedance of the chip inputs, which is ideally Rin equal to infinite, will be well above the resistor R1 and R2 values used in this circuit. This means that the current flowing in the resistor R1 and R2 is the same. The voltage at the inverting input is formed from a potential divider consisting of R1 and R2, and as the voltage at both inputs is the same, the voltage at the inverting input must be the same as at the non-inverting input. It means that Vin will be equal to Vout multiplied with R1 over R1 plus R2. Hence, the op-amp gain equation for the voltage gain of the circuit AV can be taken as AV is equal to 1 plus R2 over R1. Op-amp gain is very easy to determine. The calculations for the different circuits is slightly different, but essentially both circuits are able to offer similar levels of gain, although the resistor values will not be the same for the same levels of op-amp gain. That's all for this video session. Join me again in my next video.